Every second, we're pushing massive amounts of data through fiber optic pipelines. But the real bottleneck isn't the hardware, it's the rules governing the traffic itself. For 40 years, the Transmission Control Protocol, or TCP, has been the absolute foundation of this network. It was engineered in an era of monolithic mainframes and wired connections, designed to prioritize strict delivery guarantees over sheer speed. That reliability comes with a strict latency tax. Before a single byte of actual website data can be sent, a traditional TCP connection requires multiple round trips just to negotiate the connection and secure it. Google engineered the QUIC protocol to bypass this exact delay. By rethinking the connection sequence, QUIC cuts that setup time down from a typical 150 milliseconds to just 30 milliseconds, or in many cases, absolute zero. Achieving this required a radical engineering decision, abandoning the TCP stack entirely. Instead of fighting TCP's rigid rules, QUIC is built on top of UDP, a lightweight connectionless protocol. This moves the complex logic of reliability and ordering out of the operating system kernel and up into the application layer, forming the backbone of HTTP/3. Moving to UDP allows QUIC to systematically dismantle the three biggest constraints in modern networking. First, sequential handshakes. Second, head-of-line blocking. And third, single IP dependency. The architectural limitations of 1980s-era transport logic are now colliding with the demands of modern data, requiring a move toward user space protocol implementations. This split-screen timeline illustrates the connection sequence. A standard TCP handshake is strictly sequential. The client sends a SYN packet, the server responds with a SYN ACK, and the client acknowledges it. Only after this 50-millisecond exchange is the connection state established. But modern traffic requires encryption. Because TLS sits entirely separate from TCP, it forces its own discrete handshake. The client and server must exchange cryptographic keys before any actual application data moves. You are now 150 milliseconds deep into a connection, and the user screen is still blank. QUIC collapses these layers. It integrates transport routing and cryptographic security into a single unified action. When a client initiates a QUIC connection, that first packet carries everything required: the connection setup parameters, the TLS 1.3 key exchange, and even the initial application data request. For clients returning to a server they visited before, QUIC takes this efficiency a step further with zero round-trip time, or zero RTT. The browser remembers the secure parameters established during the previous session. On a repeat visit, it uses those cached credentials to begin sending encrypted data immediately, entirely skipping the negotiation phase. By remembering the server, the connection overhead drops from 150 milliseconds down to zero. The client downloads the web page the exact moment they hit enter. Removing these sequential blockers cuts out the largest single source of dead time in web requests, pushing the time to first byte down to the hard physical limits of the network. Once connected, TCP imposes another structural constraint. All data must flow through a single, strictly ordered pipeline. Every byte must be delivered in the exact sequence it was sent. When you load a complex web page, the server sends down various resources: HTML, CSS, JavaScript files, all stacked sequentially inside this one stream. If a network glitch causes just one of those packets to drop, say a piece of CSS, the entire TCP pipeline halts. It doesn't matter if the JavaScript and HTML packets behind it arrived perfectly intact. The protocol refuses to process them until the missing CSS packet is successfully retransmitted. This is known as head-of-line blocking. Because of one dropped packet, the entire application buffer sits idle while the network waits for a timeout and retransmission. QUIC attacks this by natively supporting independent multiplex streams. Instead of one massive queue, the HTML, CSS, and JavaScript files flow through their own separate channels at the transport layer. Now, if a CSS packet drops, only the CSS stream pauses to recover it. The HTML and JavaScript streams keep moving, completely unaffected by the error happening right next to them. This isolation is critical for users on mobile or cellular networks, where signal interference regularly causes packet loss rates of 5 to 15%. In environments with high packet loss, this structural change alone allows QUIC to outperform traditional TCP throughput by 30 to 50%. Decoupling independent resources means that minor, localized network failures no longer have the power to freeze the entire application. TCP has a major vulnerability when it comes to mobility. It strictly identifies a connection by the client's specific IP address and port number. Think about what happens when you stream a video on your phone as you walk out of your house. Your device physically disconnects from your local Wi-Fi router and hands the connection off to a cellular tower. The moment that happens, your phone gets a brand new IP address. Because TCP relies on that exact IP to identify the session, it assumes the original connection is dead. It drops the feed entirely, triggering a full, latency-heavy handshake to rebuild the connection from scratch. QUIC circumvents this by introducing a unique token called the connection ID. This token acts as a permanent identifier for the session, existing entirely independent of the underlying network layer or IP address. When your phone switches to a cellular network and gets a new IP, it simply includes that original connection ID in its next packet. The server reads the token, recognizes the existing session, and the data continues to flow without a single interruption. This capability, called connection migration, prevents dropped calls in voice-over IP applications and stops severe lag spikes in real-time multiplayer gaming. By managing connection identity inside the payload rather than at the network level, QUIC permanently eliminates the roaming interruptions that TCP inherently creates. If you look closely at this diagram of a QUIC packet, you can see how these mechanics are implemented at the byte level. The structure is divided into routing flags, the unencrypted connection ID, and the data payload. Inside that payload block, QUIC uses specific identifiers to dictate exactly where the data belongs, listing the specific stream ID and the exact byte offset for the file being transmitted. These offset markers function like file pointers. As packets arrive out of order, the application can buffer them and reassemble the file asynchronously, rather than halting to wait for the proper sequence. And everything inside this payload is strictly encrypted. Unlike older protocols where encryption is an optional add-on, QUIC enforces TLS 1.3 natively. There is no clear text version of QUIC. By extending that encryption to cover even the packet numbers, QUIC blinds intermediate network hardware. Middle boxes cannot snoop on the traffic, and attackers cannot inject spoofed acknowledgments to disrupt the connection. But perhaps the most impactful engineering choice is where QUIC runs. TCP relies on congestion control algorithms, like slow start, which are hard-coded deep into the operating system kernel. Because QUIC operates in user space on top of UDP, developers can update or completely swap out congestion control logic at the application level without waiting for a global OS update. Instead of relying on decades-old aggressive algorithms that respond poorly to latency, engineers can instantly deploy modern, bandwidth-sensitive models like BBR. Extracting protocol logic from the kernel empowers server environments to iterate, test, and deploy network optimizations at the exact same pace as modern software development. This comparison matrix highlights the specific performance delta, a 75% reduction in handshake time, parallelized resource delivery, and session persistence across changing network interfaces. Standardization as RFC 9000 by the Internet Engineering Task Force marks QUIC's transition from an experiment to the global foundation of the modern transport layer. This chart shows QUIC's transition into the mainstream. Today, it routes more than half of all internet traffic. Every major infrastructure provider, from Google Cloud and AWS to Cloudflare and Fastly, has adopted HTTP3 and QUIC as their default transport layer. For developers building modern APIs and web services, this requires a shift in architecture. Applications must be deliberately engineered to utilize independent parallel streams to actually benefit from the protocol. For network engineers, it means overhauling monitoring systems. Your security tooling must now adapt to analyze dense, UDP-based, heavily encrypted traffic, where traditional packet inspection simply fails. By decoupling connection state from the IP tuple and moving stream management to user space, QUIC aligns network architecture with the demands of a high-latency, mobile-first web.